without. What I'm going to what I'm going to speak about today is in the second part of the talk. Yesterday we focused mostly on clustering, which, apart maybe from Gaussian processes, is certainly the main application of Bayesian nonparametrics right now. And today I would like to try and give you an overview of what else there is. And basically there's two ways that I could approach that. So I could either try to give you a list or go through a lot of different models that we have. And I'm not going to do that because I think you're going to see some of these models in other lectures. And also I personally just feel it's more helpful to look at concepts rather than lots and lots of different examples that are not really tied together. And so what I'm going to do instead is I'm going to talk about how we can construct nonparametric Bayesian models for a given problem. Of course, in 2 hours I can't talk. I can't tell you too much about it. But basically, I would try to give you a few ideas of what is involved in constructing, designing a new nonparametric Bayesian model when you have a problem for which the models that are currently around don't fit. Okay. The volume of the microphone? Is that possible? Yes. Yeah. Okay. Is that better? Good. So I'm going to spend the first part of the lecture talking about constructing new nonparametric models, and that involves so one way of doing that is by taking models that already exist and modifying them in a certain way. Yeah? So there are ways to stick these models together to build more complex models, which is called hierarchical modeling. There are ways to make these models dependent on something, like on a covariate, on time, for instance. And then when we want to design models which are for which there's no modeling primitive available, then we have to think about how we represent models in the first place. So the problem of representing nonparametric Bayesian models is very closely tied to the problem of constructing them. And then I'm going to talk a little bit more about exchangeability, because if we have more general types of data, if our data does not come in form of a sequence, then we cannot simply ask, is that sequence exchangeable? We have to find some substitute for that. And depending on how much time we have left in the end, I'm going to talk a little bit about asymptotics, which is basically efforts in mathematical statistics to evaluate mathematically how well these models perform or how accurate they are. Okay, so the first way of constructing models is building new models from models that we already have. Yeah? And one way of doing that is by means of hierarchies. So the idea of a hierarchical model is the following. If you remember what we did when we just defined a Bayesian model, we start with the joint distribution of some data. Yeah? And now we assume that the data is explained in some way by a parameter. That was the picture that we looked at yesterday, right? Where we have some pattern that underlies the data. So that is our parameter theta here. Okay? And so we assume that in Bayesian modeling that this parameter is a random quantity. So we have a prior distribution on it, that is Q. And now our distribution of the data is decomposed into the distribution of this parameter and then the distribution of the data given the parameter. Right? So this is the prior, this is the likelihood. Now the idea in hierarchical modeling is that you recurse and apply the same decomposition to the parameter. Okay? Now we assume that we have some first layer of parameters here, which I call psi. They have some distribution. We sample from that, plug it into another distribution, and given psi, we sample theta. And then we use theta as our parameter in the same kind of model. Okay. Now, obviously, the parameter is not observed. So how can we do that? How can we take an unobserved quantity and split it up into further unobserved quantities? If you remember how we did Gibbs sampling for the Dirichlet process mixture model, then you will remember that we were using this latent variable trick to actually sample from theta, right? We actually, in the Gibbs sampler, we actually produce something that represents samples from theta. And so we can use these samples from theta in algorithms and treat them as if they were data, and then apply the same trick here backwards. Okay, that is a rough idea. Now, what does it mean to have a hierarchy? Here's one example, which is a hierarchy of Gaussian processes. You just heard John talk about Gaussian processes this morning. So what if we do this here with a Gaussian process? Yeah? And the idea is, or basically an interpretation, a way to interpret these hierarchies is in terms of some kind of information sharing. And I'm saying some kind of information sharing because what exactly or how exactly information is shared really depends on what kind of model you're using in the hierarchy. And for a Gaussian process, you can that works like this. So I have a picture here which is not. I'm sorry, this is not as visible as as it should be. I hate it when people say that in talks, but sorry, it just happened to be. So this is. I've taken this picture from the PhD thesis of Sinead Williamson, who was Zubin's PhD student, and what we see here is here we have a Gaussian process. Okay, this is a function drawn from a Gaussian process, and this function has a large length scale. So we produce this function by sampling from a Gaussian process, which has a large bandwidth parameter. The kernel is parameterized to have a large bandwidth. So functions that we draw from it oscillate at a slow rate. Okay, and this function has zero mean, right? So it oscillates slowly with the axis as its mean. Okay. All right. So that would be the function we draw from this model here. And now we plug this function into another Gaussian process and use it as a mean function of that Gaussian process. And we give that Gaussian process a smaller length scale. So something that we sample from that will oscillate at a higher rate. But what will it oscillate around? Not the axis anymore, but rather around this function. Okay. So we get something that looks like these small wiggly functions here. Yeah, these red and green functions. So that way we can model a problem where we have two time scales. Yeah, something that oscillates on two time scales, once rapidly and then on a larger time scale, and we can split these up. Okay. Okay. Now the most widely used hierarchical model in Bayesian nonparametrics, I suppose, is the hierarchical Dirichlet process, and that model works like this. So we remember when we sampled from a Dirichlet process here, this was the formulation of the parameterization of the Dirichlet process we saw yesterday. We have this parameter alpha. That was the parameter which controlled how probable it is to produce a new cluster. And then we have this parameter G naught here, which is the distribution of the atom locations, right, of the cluster parameters. And we now sample. The idea is now that we sample the measure which controls the locations of the atom locations, again from a Dirichlet process. Okay, usually this is a parameter that we choose, but now we do this hierarchically and we sample this measure itself from a Dirichlet process. Now I've drawn that over here, so you see this picture here, this is a sample from, or represents a sample from a Dirichlet process, or rather part of a sample, namely finitely many clusters, or finitely many atoms. So the locations here on the interval, these are the locations of the atoms, what I called theta yesterday, right? So in this discrete random measure is the location of the Dirac spikes. And the heights of these bars here are the weights, which correspond to the cluster sizes or the cluster probabilities. Okay. So these are locations of cluster parameters or values of cluster parameters and probabilities of the corresponding clusters. Okay. All right, and now we take this discrete measure here, we plug it into a Dirichlet process, and we sample from that. And what's going to happen if we do that, each time we produce a new cluster, we draw it from the measure given here, and that is itself a discrete measure. So we will always, when we produce a new cluster, we will always produce a point that we have already seen in this measure here. Okay? We have restricted the possible values of cluster parameters to these values. And so you see that these are two different samples from that, and you see that the locations here are exactly the same as up here. But what's the point if nothing changes? Well, something changes, and those are the weights. Because we sample from this, but we sample from this at random, and these are not the number of points that we actually see. These are the probabilities, right? So we sample from that, and we get different weights here. Okay. So why would you want to do something like that? Yeah. An application of this is a non-parametric version of latent Dirichlet allocation, yeah? which is a topic model. Now, I don't expect everybody here to know what latent Dirichlet allocation is. I suppose a lot of people probably do, but basically what you want to do here is, so in topic modeling, kind of the basic idea of topic modeling is that if you want to, if you do natural language processing and you want to represent a topic, a good way to do that is as a distribution over words. Yeah? So that is the basic assumption of topic modeling. Topics are distributions over words. And that means you, when you analyze a big corpus of text data, you basically extract all the words that occur in the data, and then you record how many times does each word occur. And that gives you an estimate of a probability distribution. And the idea is now that, remember yesterday when we talked about these power laws, we said, well, in language, there are some words that occur all the time, and then there are some words which occur only rarely, right? And many of these terms are specialized. Now, if you focus on a specific topic, right, if you have some biological term, overall in the language it will occur rarely, but in the context of biology, it will be more frequent. Yeah? And the idea is that you can use these frequencies to characterize as a complete characterization of a topic. Okay? So a topic, in technical terms, what does it mean? A topic is a vector that represents a probability. It's a probability over all words, so it's a very long vector. Each entry corresponds to one possible word. Yeah? But it's finite length, and the entries are numbers, non-negative numbers which sum up to 1. Yeah? So it's a probability distribution over a finite number of events, and these are the words. Okay. And then when you sample from that, you use that as the parameter vector of a multinomial distribution and sample from that multinomial. Okay. And now one way that you can so in topic modeling, if you want to represent documents, you represent them in terms of mixture models. Yeah? Or that was an idea that started in the late 1990s with a model called probabilistic latent semantic analysis. And that is very simply, it's a mixture model of multinomials. Yeah? And the way it works is you first sample the index of a topic. The topic is characterized by this probability distribution over words, and then you sample the document from this probability distribution. Okay? So that's a mixture model representing documents. And this model latent Dirichlet allocation here was introduced based on the idea that using a simple mixture model is very restrictive, because what is the assumption in there? The assumption in the mixture model is every data point belongs to one cluster, right? And so topics are clusters, and that means every document belongs to exactly one topic. Yeah? And that is really not such a good model of documents, because usually you have some mix of topics in a document. And actually you can now say, okay, that is maybe an asset. Maybe you can use the same idea that we use to characterize topics and say documents are actually characterizable as mixtures of topics. Okay? Just as document or as probabilities over topics, just as topics are probabilities over words. And this is this idea in latent Dirichlet allocation. So you want to represent documents as by a combination of topics. Yeah? And you can do that in a non-parametric way using exactly this idea here, this hierarchical Dirichlet process. So what do we represent here? These locations of the atoms are topics. So basically what you have to imagine down here is a set of finite probability distributions. Yeah? It's a set of very long vectors that represent these are down here. And now we sample a bunch of these at random using a Dirichlet process. These are our topics. And then these topics will, these here, yeah, okay, so what are the heights of these? These are the probabilities of this topic in the overall amount of text that we have, yeah, in the library. And now these here, these distributions represent individual documents. And you can see that we have the same topics, so the same topics that are characterizing our text corpus, but each document is characterized by a different probability of the individual topics occurring, okay? Okay, so you see that we have been, if you compare this here, this way of sharing information between these different draws here, and this way of sharing information, it's two very different things, right? In one case, here, what information do we share? We share the information of this mean function between these different functions which oscillate at a higher rate. And here we share the information about these locations, which is very different because this is a discrete mathematical setup. Okay? But both of them are instances of this idea of hierarchical modeling, where you split up your parameter further to express something that some characteristic that things have in common, which is the parameter at the upper level of the hierarchy, and then a finer distinction, which is the medium level of the hierarchy. Okay, and you can use a lot. You can basically take all kinds of Bayesian nonparametric models and use them as building blocks or as modules and stick them together in these kind of hierarchies. Yeah, and you don't have to be encyclopedic about it, but you can very flexibly build models with that. One thing that and why is that possible? Why is that particularly possible with Bayesian models? Because of Gibbs sampling, in a sense, right? This is possible because we can Gibbs sample our way through that hierarchy. Yeah? If you can sample the individual components of the hierarchy, then you can sample the entire hierarchy. Okay. One word of warning about that. If you do that, one thing you have to be really careful about is that as you increase the number of layers in the hierarchy, the model becomes more and more complex, and sampling also becomes more and more complex. The state space that your sampler has to explore becomes much more, it just becomes much larger each time you add another layer in the hierarchy, right? And so you have to sample, if you have 3, 4, 5 layers in your hierarchy, then you no matter how long you sample, you may just never actually see the sample that comes from your true model, yeah? Because the Gibbs sampler just hasn't mixed yet. Okay. Good. So this is one way how you can build new models by reusing models that we already have, yeah, as these building blocks. Questions about that? Okay. So the other way of building models from models that we already have that I would like to mention, I mean, this is not that these are the only ways, but I just want to focus on these two, are so-called covariate dependent models. And the setting here is the following. We have, remember we were looking for a parameter or a pattern that explains our data. And now we assume that this pattern depends on some kind of covariate, say on time or on space. Okay? And an example is, yesterday I had a simple example of image segmentation. And the corresponding example here would be video segmentation. So you have a sequence of images which are indexed by time. And you want to segment that sequence. Okay? And now a solution of that, so here I have 3 frames from a video. And here are the corresponding 3 segmentations of that. Now, these pictures here, these images change smoothly over time. Right? And you would like the solution to reflect that. Each individual solution here is a segmentation of the individual image. And we saw yesterday that we can do that by means of clustering, right? So each individual solution is a clustering, but we would like these clusterings to be tied together over time and change smoothly, okay? And if we again write out the basic object that we had that we looked at yesterday, this discrete mixing measure, that underlies the clustering or that underlies the mixture, right? Remember, we had this mixing measure M, which completely summarizes the parameters that occur in clustering. So the locations of the atoms and the weights. Yeah, this is, I was sitting in the back this morning and I realized that actually the lower quarter or so of the slides is not visible. So I'm sorry, I wish I had realized that earlier, and then I would have changed my slides. So, yeah, okay. If something really important comes up at the bottom of the slide, then I will probably have to write it on the board. Okay, so basically we have this mixing measure that describes the clustering. And now if we want this to depend on a covariate, we have to make it a function of that covariate. Right? So if we want a clustering solution to vary smoothly over time, the solution is described by the parameter values of the individual clusters and their weights. So we have to make these parameters and these weights a function of time, okay? Or of space, or whatever else we would like to use as a covariate. And there is a model called the dependent Dirichlet process, which is extremely popular in nonparametric Bayesian statistics. It's not used so much in machine learning, but in machine. So I think that just is a matter of topics that people focus on. In machine learning, one big application of nonparametric Bayesian modeling, for example, are topic models and natural language processing. So the tools that get used a lot are things like hierarchical Dirichlet processes, because of the topic models, and the Pittman-Yaw process because of this power law property and so on. Whereas in nonparametric Bayesian statistics, people are interested in all kinds of applications where you have this covariate dependence. And this model is, you know, in some senses it's actually maybe a bit of a hack, but it's just, you know, it's just hit a nerve, and it's maybe the most popular modification of the Dirichlet process in nonparametric Bayesian statistics. So what we do here is we have these parameters, the cluster sizes and the cluster locations. And as I said, we're now making them functions of the covariate, right? And we know that these cluster weights, that they are between 0 and 1. And now they take as input, they take a covariate value, so say time. And so that becomes a function from the time axis into 0, 1. Okay? And we have to think about how we can model that function. And similarly, for the parameter values, we have a function from time into the set of possible parameters, yeah? Cluster parameters. Okay, and now the idea in the dependent Dirichlet process is if we have to model smooth functions here. So why do we use a Gaussian process? Okay. If for these cluster weights here, that is a bit of a problem because, as John told you this morning, when we use the Gaussian process and we look at one particular time point, right? The Gaussian process gives us a random function, and now we fix one time point and we look at the function value at that time. What is the distribution of that function value? The function is random, so that is a random variable. What is the distribution? It's a Gaussian, because it's a Gaussian process, right? But a Gaussian is a distribution on the real line. And what we want here is something that is in 0, 1, right? We don't want something that is on the entire real line. So we have to somehow transform this, and also we want to have a specific distribution here if we want to have a Dirichlet process, because we know in the Dirichlet process, stick breaking construction, these weights have to be beta variables. Otherwise, something else is going to pop out, right? Okay, so we have to transform this Gaussian to have these Gaussian variables at each time point to have a marginal distribution that is beta. Yeah? And so you have to, and that is why I said it's a bit of a hack, because you have to sample from a Gaussian process and then put it through a transformation that turns it into a beta. That is possible by means of cumulative distribution functions, but it's just a bit computationally intensive. Yeah? Okay. And then similarly, we look, so what we do specifically is that we use the stick breaking construction. We sample these proportions, if you remember, that we use to construct the weights. We sample the proportions proportions from the Gaussian process, turn them into beta variables, and then applies this formula for computing the weights from the stick breaking construction. Yeah? So the idea is make a Dirichlet process dependent by look at the components that occur in the stick breaking construction and turn them into functions that vary smoothly on time. Okay? And these functions have to have the right marginal distributions at each time point so that a Dirichlet process comes out. Yeah. Okay. So if we do that, what do we get? We get a distribution that is, if we fix a time point and look at the marginal clustering, the distribution of the clustering that we get at that time point, say for one frame in the video, that distribution is actually a Dirichlet process. Yeah? And these clustering solutions vary smoothly in time, and how smoothly depends on how we set the covariance function of the Gaussian process. Okay? All right. And so the kind of, this is specific to the Dirichlet process, of course, right? This uses this very specific construction definition of the stick breaking process for the Dirichlet process. And but you can, if you just look at this idea here, you can generalize this, and the general theme is that we have some random object, yeah, that has a certain distribution, and then we have our covariate space. So the random object is, say, the discrete random measure. Then we have a covariate space, time space, or whatever that is supposed to index that. And we have to turn this into a random function that maps into the set of possible random objects. Yeah? That is kind of the general idea. Okay. Good. So now we have seen with today's my talk yesterday and John's talk this morning, and what I've shown you so far, what we have seen is we have seen a bunch of models. We have seen the Dirichlet process, the Pitts-Niort process, the Linear-Buffet process. We have seen the Gaussian process, and we have seen ways of how we can combine these models together. Yeah? And with that, we can that accounts for actually for most of the models that we have in Bayesian nonparametrics in one way or another. Yeah? And when EY and I gave a NIPS tutorial on this last December, EY made this list here because we figured it would be nice to just have a list of all models and relate them to the applications and to what type of parameter we are using. Yeah? So remember, in the Bayesian model, the intuition that I tried to convey yesterday is that the parameter is some kind of pattern that explains the data. What type of pattern do we use and what do we get? Yeah, so we have classification and regression models. In that case, the parameter is a function, and the prototypical model for that is a Gaussian process. Right? Then when we do clustering, the pattern is a partition, and so the model for that is the Chinese restaurant process or a Dirichlet process. Right? There's this analogy between the two. We can also use the Dirichlet process for density estimation, and so on and so forth. Right? We can do this hierarchically and okay. But what you can see here is that if you go through this list, there's a certain set of basic models that we use to generate all of these different models. Yeah? And what I want to do next is I want to talk I want to use a few slides to talk about what we can possibly do if we want to go beyond that. What would be involved in that? How difficult is it? I can tell you it's not easy to do that. And in order to do that, I have to talk about representations for a little bit. So, usually when we, in parametric statistics, when we want to build a new model, then what we do is we write down a density, right? That is how we define a probability model. We write down a density. And one of the real obstacles in designing nonparametric Bayesian models is that doesn't work. Yeah? You can't just write down a density. And the reason for that is the following. What is a density? What does a density mean? A density is a representation of some probability measure, or measure in general, but let's say it's of some probability measure with respect to another measure. Yeah? And what does this what does this formula mean? So this here, for example, imagine that this here, say, is a Gaussian distribution on the line. Yeah? And this here is Lebesgue measure, which means a uniform distribution on the line, something flat distribution. And this here then is a Gaussian density. Yeah? So what does this density mean? It tells us how we can reweight this distribution here at each point. It's a point-wise reweighting formula to turn it into a Gaussian distribution. Okay? And it's very neat to work with densities. Densities are very convenient because they are defined point-wise. Yeah? If you have ever seen any measure theory, then you know that measures are functions that are defined on sets. So we have to take the real line, and now, okay, take the real line, put a measure on it, draw it. How do you do that? You can't actually draw it because what you have to draw on your x-axis are all possible subsets of the real line. And then you would have, for each of them, you would have to draw a value. You can't do that, right? But this representation here is something that actually is a function on the domain on which our measure lives. So that's very convenient. Okay. Okay. Now, but the problem is that that in order for this representation to be useful, we need this distribution here. Okay. So the first problem is if we have some parameter space in Bayesian nonparametrics, some infinite dimensional space, and we want to define this distribution on that space, then we first need some other distribution on that space to write down a density, right? Some reference distribution, which is usually that is called a carrier measure. Sometimes just a reference measure. Okay, so we first have to, we first have to solve the problem of how to put a distribution on that space anyway. Okay, that is the first problem. The second problem is this measure here should have certain properties. So if you represent a Gaussian distribution, what do you use here? You always use something uniform, right? And for good reason. Why do you not use another Gaussian? Because if you use another Gaussian, then this density is much harder to interpret. Yeah? Imagine we take two Gaussians which have peaks at different locations. Now we could represent one of them as a density with respect to the other one. That's possible. Yeah? But what would this density look like, or what would it mean? If this density is very small at some point, what does it mean? It could mean, in this case here, it always means this probability measure has small probability mass in that region. Okay? If we use another Gaussian here with another location, it could either mean that, or it could mean this one is very large in that region. Right? Does that make any sense? So if we do something, if this distribution is not flat, then if the density increases somewhere, it could either mean that this distribution becomes larger, but it could also mean that this one becomes smaller. Yeah? So you would like this to be flat and neutral, yeah? Just to get some sense of interpretability. And such uniform distributions, it turns out in mathematics that such uniform distributions only exist on certain spaces. And roughly speaking, these are finite dimensional spaces. So that exactly rules out the parameter spaces in Bayesian nonparametrics. Yeah? The technical term for these flat distributions or uniform or neutral ones is translation invariant. If you just take it and shift it around on your space, then that doesn't change the value. Okay? And that just doesn't work on infinite dimensional spaces. Yeah? But remember, the parameter spaces in Bayesian nonparametrics are always infinite dimensional. So we can't do something like representing the prior or the posterior as a density with respect to something nice. Yeah? And the second problem is, in order to do that, we first have to define some probability distribution on that anyway, with respect to which we can represent it. It's kind of a cat bites its own tail problem. Yeah? Okay, so that's the first representation problem that we have to cope with. And there's another one. And the second one is, so I have, yesterday I talked about all these clustering models, which are all Bayesian models, but you may have noticed that throughout this whole part on clustering, we didn't see a single Bayes equation. Right? Now, usually when you define a Bayesian model, or when you see the definition of a Bayesian model in a textbook, it's defined in terms of the Bayes equation. Right? The Bayesian model is like the Bayes equation. The different parts of the Bayes equation are the Bayesian model. But the reason why I didn't show you any Bayes equations yesterday is because for these non-parametric models, Bayes' theorem is actually not applicable in most cases. Yeah? So they don't have a Bayes equation. They are still Bayesian models, but they don't have a Bayes equation. Let me try to explain what I mean with that. Okay. So in general, the Bayesian model is given by a prior distribution, a likelihood, and a posterior. Yeah? And these are simply defined as conditional probabilities. Yeah? So we have a data random variable, we have a parameter random variable, and then we have the distribution of this parameter random variable. We have the conditional distribution of the data given the parameter, and the conditional distribution of the parameter given the data. And these are the components of the Bayesian model. Yeah? So they are defined as the conditional probabilities of these quantities. Now what the Bayes equation says is, under certain conditions, you can relate these quantities together in this nice way that we all know as a Bayes equation. Yeah? But they are not defined in these terms. These are just abstract definitions. Yeah? So on the upside, that means we can define this without a Bayes equation. On the downside, it means abstract means we can't handle that. We have to find some way to handle that. Okay. Now the Bayes theorem says, if usually the Bayes equation is written as a ratio, right? You have the posterior on one side, the posterior density on one side, and then on the other side you have the prior density times the likelihood density divided by the evidence density, right? That's a quotient. But if you look at that from a slightly more abstract point of view, then the Bayes equation is actually a density in the following sense. So here we have the posterior probability, and this is a conditional probability, okay? And then we have the prior, which is also a conditional which is an unconditional probability. And Bayes' theorem in the way it's used in mathematical statistics is the density of the posterior with respect to the prior. Okay? So remember on what I just said before on the last slide, the density is a rule that tells us how to take one probability distribution and reweight it to turn it into another probability distribution. Now what this here says is we have a density that is parameterized by the data we have observed, and which tells us how we have to reweight, given this data, how we have to reweight our prior distribution to give us a posterior, given this data. Okay? And now that is simply what we would like to compute. And Bayes' theorem tells us this density has a specific form, and it is given by the likelihood, the density of the likelihood with respect to the evidence. Yeah? So that is this quotient that we get in Bayes' theorem. Yeah? So basically what Bayes' theorem says is we have these abstract quantities, we have no idea how we can handle them, but under certain conditions, which hold in parametric statistics, under certain conditions, we can nicely express the relation between this and this as a quotient of densities. Okay? All right. And that provides us with a concrete connection between the prior and the posterior. That is not the same problem. Yeah, okay. So when I say this doesn't always exist, that is not the same problem as posterior tractability. Yeah? I mean, you might have heard that there are problems with computing the posterior in Bayesian statistics. But that is because you have to compute this quotient, and it contains an integral. Yeah? The evidence term in the denominator is an integral, and that can be hard to compute. That is an entirely different problem. Yeah? This is not about whether this is hard to compute. This is whether about this quantity exists or does not. Okay?
So is that because the posterior is not absolutely continuous with respect to
exactly.
And when does this? Are you going to show examples when this happens?
So for the Dirichlet process, for example, it happens. I don't want to go into too much detail because it gets a bit technical. But basically, the problem is that these non-parametric models can get the posterior is a family of distributions, right? You get one different probability for each possible observation here, and basically in these non-parametric models, the this family can get too large and diverse. So that what you want to have for, or what you would need to have for this equation to exist is that every single element of this family is absolutely continuous with respect to the prior. And basically these families are too large and diverse for this to be possible for all elements. The only way that you could get that is by making this measure here infinite, or non-sigma finite. And models for which, so basically models for which families of distributions for which that is not possible, to make them all absolutely continuous with respect to one distribution, are called undominated models. Yeah? And so otherwise, if that is possible, then you say that this measure dominates the family. Yeah? And one example of that are Dirichlet process measures, or basically all the measures based on random discrete measures that we saw yesterday. Yeah? So Dirichlet processes, Pittman-York processes, all these distributions. And essentially, intuitively, the problem is that these, because of the discreteness, they can put their mass at individual points, but the space has an uncountable number of points. So there is an uncountable number of possible patterns where they can place their mass. And if you would like to have a density like this, then what you would need is a measure here, which puts positive mass at every single one of these points. Yeah, and that's just too much. Okay. Okay. I'm not going to dwell on this further, but if you're interested, you will just have to look into the literature and read it out. And I know it's not easy. I went through it at some point. I can tell you it takes its time. But just the message I want to convey is, in Bayesian nonparametrics, you really cannot think of a Bayesian model as being defined in terms of a Bayes equation. Yeah? It's really the other way around. You define a Bayesian model. If you are lucky, it satisfies a Bayes equation. And that tells you how to get from the prior to the posterior. In Bayesian nonparametrics, it often doesn't work. And then we have to find some kind of substitute. We have to find some way of connecting the prior to the posterior. And it would turn out that the way that is done in Bayesian nonparametrics is conjugacy. Yeah? We will get back to that like 2-3 slides on. Okay, so I'm now going to spend 3 or 4 slides trying to tell you how these problems can be addressed. Yeah? And I also want to use this as an opportunity to try to show you how the Gaussian process and the Dirichlet process are related to each other. Yeah. Okay, so this morning you heard John talking about the Gaussian process, and he told you, if you recall the definition, the Gaussian process is a distribution that gives us a function. It's a distribution that on random functions, right? So we have a random function that we sample from the Gaussian process, say, on the interval AB, and which maps to R. Okay, and that means that if we use this as, say, a non-parametric regression, then the patterns that we're using are continuous functions. So the parameter space of our model is the set of continuous functions on AB. Okay, and I have a picture here where we see a bunch of samples from a Gaussian process, which are these functions, and then here, where they all shrink to a single point, that's where observations are. Yeah. So this is conditioned. This is posterior conditioned on observations, and at these few points where the observations are, we exactly know the value, and otherwise we're uncertain. Okay. So here at this specific point, we have a location S between A and B, and this is the function value of the random function at that point. Okay. So now recall the definition that John gave you. That is, we call this a Gaussian process. We call this function a Gaussian process if the following holds: if we can take any finite subset of points down here, yeah, and we look at this vector here. So we take the vector of function values at this finite subset of points. Now, since the function is random, this is a random vector. It has a probability distribution, and we say that this is a Gaussian process if this distribution here is a Gaussian. with d dimensions because it's a vector of max d. Yeah? Okay. Now, if this is a definition, and John said already this morning that this object exists is not a triviality. Yeah? It's not by any means clear that this object should exist. But the intuition behind this construction, or because the results which guarantee that this actually works, is the following. If you imagine we start from a Gaussian process like this, right? And we look at these possible distributions that we get for different sets of points here. Then these distributions are all related to each other in some way, right? They can't be arbitrary because they are all marginal distributions of one and the same infinite dimensional probability distribution, right? So in particular, if we take some set of points here and look at the distribution that we get from that, and then we take a subset of these points and again look at the distribution that we get from that, then the second distribution will be a marginal of the first one, right? Does that make sense? Okay, so these distributions are all marginals of each other. If we take two sets that overlap, two sets of points that overlap, then once again, the marginal on the common set of points, the two marginals on the points that they have in common will coincide. Yeah? So we have a kind of coherence condition between these different distributions that we get for different sets of points down here, that they all have to marginalize to produce each other. Okay? That is simply because they are all marginals of one and the same Gaussian process. Okay, now if we know all these distributions here for all possible sets of points, then we can ask conversely, if we start with these distributions and they have this coherence property, that they are all marginals of each other, does that define a Gaussian process? And there are results in probability theory that are called extension theorems or projective limit theorems, which guarantee that that is actually the case. Yeah? So the idea is you have a one-to-one correspondence between a single infinite dimensional distribution and an infinite family of finite dimensional distributions. Okay? All right, you need some, you have to be careful with these kind of results because you have to do some extra work to make sure that what you sample from that is actually a continuous function. You can, this defines, using this, it gives you a distribution on functions, but you would like to have more than that. You would like to have a continuity property, and that is a bit harder. But I cannot tell you how to do that without starting to talk about things like topology, and I think you will be all glad if I don't do that. So I will avoid it, okay? Just as a warning. Now, but basically the idea is you can define a stochastic process, so a probability distribution on an infinite object or an infinite dimensional object by means of by all its finite dimensional marginals. Yeah, that is the basic idea. And for the Gaussian process, this is the definition that we always use for the construction. Think of this as a construction that we always use. And I said before that we have this problem that we don't have density representations for these models. Now this here is a representation, right? It's not a density, it's not as nicely written. We are not able to write it down as nicely as a density, but this is a representation of an infinite dimensional distribution. And this is in fact, these kind of results are the most generally applicable substitutes that we have for density representations on stochastic processes. Okay? Okay, now can we do something similar for the Dirichlet process? Yes, we can actually. Yeah. So we can. Yesterday I showed you this nice, simple constructive definition of the Dirichlet process, which tells us simply how to sample this discrete random measure piece by piece. Yeah? But we can use a similar construction as for the Gaussian process. In the Gaussian process case, we have constructed a random function theta, and now theta is a random measure. So I called it theta here again, right? Because it plays the same role, but it's this random measure and random discrete measure. Remember the sum over the weighted sum over cluster locations. Okay. All right. So now the corresponding result to this construction of the Gaussian process is this: we have to find in the Gaussian process case. Here in the Gaussian process case, what we did, we looked at marginals, and how did we get the marginals? We chose points down here, and then restricted ourselves to these points. Yeah. For probability measures, that's not really very helpful because they are not, you know, they are functions on sets, right? So this random function is a function on points, but the probability measure is a function on sets. Or put differently, for like say a continuous probability measure, if you put it in a single point, the probability is always 0, right, for a Gaussian set. So that's not very helpful. And so what we do instead is to get the marginals, we don't use points, we use sets. Yeah? And once again, we want the marginals to be finite dimensional, so we choose a finite number of sets. And we choose sets which partition our space. So imagine that this square here, or this rectangle rather, is the space on which we would like to put a Dirichlet process or some other random probability. Okay. Now what do? We partition it into a finite number of sets, which I have called A1, A2, A3, and so on here. So we can write these sets into a vector. Yeah, together they form the whole space. And now we take our random probability measure and we evaluate it on each of these sets. So just as before, we took a random function, we plugged in a point. Now we take a random probability and we say how much probability does it put on set A1, on set A2, and so on. And that gives us a vector. Which properties will this vector have? Well, it's finite, right? All these entries here are probabilities, so they are all between 0 and 1. And they will sum up to 1 because these sets together form the entire space. Right? So that is now our analog of what we did before. So the intuition that John mentioned this morning is take a vector and think of, as you make this vector larger and larger, it becomes something like a function, right? The infinite limit, it becomes the vector becomes a function. Yeah. This here is the analog of that. We have a finite probability distribution. Now we make this partition into sets here. We make that finer and finer. Make the set smaller and smaller. We get a larger and larger vector, and that you can roughly think of that as converging to a probability measure. Okay. All right. So once again, if we know the distribution of these sets here, yeah, if we know the distribution of this finite random vector for any possible choice of sets, then this is that together forms our family of finite dimensional distributions. Okay, so we have a finite vector here, which is a finite probability that has a probability distribution, and we can index this distribution by the particular choice of sets that we have taken here. Now we could take some different choice of sets here. We would get another vector and another probability distribution. Okay, and now what we need is we need the family of all these probability distributions for all possible partitions into finitely many sets, which are of course infinitely many. And again, if they have this property that they are all marginals of each other, then they together define a random probability measure on that space. Okay? And an example of that is the Dirichlet process. So what is the probability distribution that everybody has heard of on finite probabilities? That's the Dirichlet distribution, right? So if this vector here is Dirichlet distributed for all possible choices of these sets, then what we get here is a Dirichlet process. And how can we make sure that they all fit together in the right way? Well, we can actually look at the parameterization of the Dirichlet process, and it had these two parameters, alpha, which is the scalar, right, and G0, which is the probability distribution, right? Remember the probability of a new cluster and the probability of, or the location, probability of the atom locations. Now, we start with these two parameters, and how do we define the Dirichlet distribution? We choose, for a given partition, we choose the concentration parameter as the Dirichlet again as alpha. And then the second parameter of the Dirichlet distribution is an expectation, right? Which is also a probability vector. How do we choose that expectation? Well, we take these sets and plug them not into this random measure, but into this parameter measure. We get a vector, and we use that as the expectation parameter of the Dirichlet distribution. So if you define your Dirichlet distributions in this way, then it turns out that they automatically have this coherence property that you need, and then the model that you get out is the Dirichlet process. Yeah. Cool.
So I'm confused. The Dirichlet process, what are these sets, these A sets?
These sets here.
What is Dirichlet process?
Yeah. So say you want to define the Dirichlet process on the line. Yeah. Then these are all possible all possible partitions of the line into finitely many sets. They have to be measurable actually, but let's not worry about that. Okay? And they correspond to, here, in the Gaussian process case, they correspond to taking finite subsets of points here. Again, you have to take all possible finite subsets of points. Yeah. And the reason why we have points here and sets here is because these are the natural objects on which our random functions are defined, right? The random function we draw from a Gaussian process is a function on points that maps points to points. Here we want to have a random measure, and a measure is a function that maps sets to probability values. Right. Okay. Right, and this idea was actually used to define the Dirichlet process in the first place. So the way the Dirichlet process was introduced was in this way, and that's why it's called the Dirichlet process. Yeah? So Gaussian marginals, Gaussian process, Dirichlet marginals, Dirichlet process. Very simple. And then this much simpler definition that I showed you yesterday, the stick breaking construction, was only discovered about, well, it was only published about 20 years later. It was discovered about 10 years later and published about 20 years later. Don't ask me why. And the reason why this construction is interesting anyway is the stick breaking construction is applicable for the Dirichlet process and for a very small number of other models. So the Pittman-Yaw process also has a stick breaking construction, and a few other models have. But in general, a random measure does not have a stick breaking construction. In particular, if you want to have a random measure that is not discrete, yeah? So if you would like to do something like density estimation, then you're usually interested in something that is not discrete. For clustering, that's an asset. That's exactly what we want. We want to have separate clusters, so we want discreteness. But if you want to do density estimation, say, you would like something that is not discrete, and you cannot get a stick breaking construction for a random measure that is not discrete. Yeah? So basically, if you want to produce more complicated objects, then you have to fall back on these slightly more sophisticated constructions. Okay. Okay. So here are a few representations that are used in Bayesian nonparametrics. Yeah. So stick breaking is certainly used most often, I think. It's whenever it is applicable, yeah, because it is very simple. And another thing that is great about this is it is constructive, right? These definitions I showed you on the previous slide, both for the Gaussian process and the Dirichlet process, they uniquely define your object, right? But they are not constructive. What this here says is the stick breaking construction says it gives us a formula for iteratively sampling something that gets closer and closer to the actual object. Yeah. You can actually implement that. But they are only available for a few models, so a Dirichlet process, Pittman-Yaw process, then something I mentioned yesterday called the normalized inverse Gaussian process that also has a stick breaking construction. And this beta process that you can use to generate the Indian buffet process also has a stick breaking construction. Yeah. So like the core set of these random discrete measure models, they do have stick breaking constructions, but in general that becomes more difficult. And it is not clear in general which models do or do not have stick breaking constructions. We don't know that yet. Yeah? It will take a few more years. Then there are these projective limit constructions. So these are the constructions that I showed you on the two previous slides, where you construct the infinite dimensional object from its marginals, Gaussian process, Dirichlet process, and so on. These are the most generally applicable way to do this, and this is like the standard construction tool in stochastic process theory. But they are mathematically more challenging. I mean, I guess you already saw that on the slides that I showed you, that it's a bit more complicated. And actually, that is only part of the story, because basically to ensure that the random quantities you draw from these things have the properties that you want, you have to put in some rather subtle mathematics, usually. And then there are representations in terms of known stochastic processes. So for example, Levy process representations or Poisson process representations. Of course, these are not available for all models either, right? But basically, if you have a model that that uses something that is essentially a known form of stochastic process, then you can just fall back on work that has already been done. And what is nice about these kind of representations, for example, Poisson processes, they come with a very well understood calculus. Yeah. So you have a bunch of results which tell you, in this case, a Poisson process behaves like this. If you add them, then you get this, and so on. And you can use this whole toolbox of calculus that is already available in probability and apply it to your models if you use one of these representations. Yeah, so that's very